Hello class, today's lesson is the chemical properties of alkyl halides. In the previous lessons, we have talked about different ways alkyl halides can react. We saw that alkyl halides can react by substituting a halogen by a nucleophile under nucleophilic substitution reactions. And today's lesson is going to focus on another way of reaction of alkyl halides, where halogen together with the hydrogen or halogens only can be eliminated from the molecule and produce unsaturated molecules. Our first elimination reaction is the reaction with strong bases to produce alkenes. Alkyl halides, when boiled with alcoholic potassium hydroxide, form alkenes by elimination reaction by losing a molecule of halogen acid. If the halide is unsymmetrical, meaning beta carbons are different, this respect is Zaitsev rule. An example: 2-bromobutane reacting with the potassium hydroxide in ethanol under heat conditions will produce two products, 2-butene and 1-butene. 2-butene is a major product because it is more stable compared to 1-butene. What is the statement of Zaitsev's rule? Formally, the rule is that an elimination will occur such that hydrogen is removed from the beta carbon with the fewest hydrogen atoms. In other words, it says the poor gets poorer. The meaning of this statement: in the elimination of hydrogen halide from an unsymmetrical alkyl halide, the more highly substituted alkene product predominates. What is alpha carbon? The alpha carbon is the carbon attached to the leaving group, while the beta carbons are all carbons attached to the alpha carbon. Let us try the mechanism together. First of all, potassium hydroxide reacts with ethanol to give potassium ethoxide and water. Ethoxide is a strong base. It subtracts one of the hydrogens from beta position of the molecule. Because we have two beta carbons, it will start from one of them, and here the electrons of the bond are repelled to form a pi bond between the two neighboring carbons, which will repel the electrons of the bond between carbon and bromine, and this produces an alkene and bromide ion. Second option, the base can subtract another hydrogen from another beta carbon, and this one will produce another alkene, which is different from the first one. It means that there are two alkenes possible, and we'll have a mixture of them in the products of this reaction. But the first product will be major while the second product is minor. Why? Because the alkene where the double bond is in the middle is more stable compared to the alkene where the double bond is between the first and the second. And then the more the stable product, the more it is dominant in the mixture. What is the type of mechanism is this? We have one related determining step. And how many chemical species are involved in this step? There are two, both the base and the alkyl halide. Because both are contributing to the formation of this product simultaneously, it is the elimination of the second order or E2 reaction. So, what is the mechanism of this reaction? Where a tertiary alkyl halide is reacting with the potassium hydroxide in ethanol to produce methyl propene, potassium bromide, and water. You can see it is an elimination reaction, but which is involving a tertiary alkyl halide. In our previous example, it was a secondary alkyl halide. Let us have the mechanism together. Potassium hydroxide will first react with ethanol to give potassium methoxide and water. The alkyl halide will first undergo self-ionization to give a carbocation. The strong base, ethoxide, is going to subtract one of the hydrogen from the beta carbons, and the electrons of the base will repel electrons of the bond between hydrogen and the carbon to form a pi bond between the two neighboring carbons, which will result in the formation of an alkene. And this reaction is having two steps. And the first step is a slow step, while the second step is the fast step. Because the first step is a slow step, it is the rate determining step. And how many chemical species are involved in the formation of this carbocation? It is only one chemical species, which means that the mechanism of this reaction is E1, or unimolecular elimination, or elimination of the first order. Why do we assist to two different products of this reaction, ethene and ether? This was unexpected in elimination reaction, where we were expecting to have ethene and alkene only. The mechanism of the reaction which produced ethene is similar to the one in our first example. Can you try the mechanism of the reaction which produced an ether? Here it is. Alkoxide, instead of attacking on beta carbons, it is going to attack on the alpha carbon by donating electrons to this carbon, and the electrons of the bond between chlorine and carbon are repelled, and the chloride ion is produced together with an ether molecule. This time, the alkoxide is not acting as a base as it was in elimination. Instead, it is acting as a nucleophile because it is a substitution. Comparing elimination and substitution. The nature of the product formed depends on the solvent, temperature, and structure of the halide. In the competition between nucleophilic substitution and elimination in alkyl halides, the elimination is favored by use of high temperature and a strong base. Example, alcoholic potassium hydroxide instead of aqueous potassium hydroxide, meaning that elimination is favored in alcoholic potassium hydroxide, while substitution is favored in aqueous potassium hydroxide. Again, when low temperature and weak bases are used, substitution is favored. The second elimination reaction is the reaction of the halides with a strong base to produce alkynes. Both gemino and vicino dihalides are heated with alcoholic potassium hydroxide, sodium hydroxide, or sodium amide to produce alkynes by elimination reactions. The mechanism is exactly the same as that of monohalides. You only need to repeat steps twice. If you want to know more about this, comfort preparations of alkynes. Let us use these examples. Here we have 1,1-dichloropropane reacting with the potassium hydroxide in ethanol under hot conditions to give propane. And here we have another example where we have 1,2-dichloropropane reacting with sodium amide in ethanol under hot conditions to produce again propane. The third elimination reaction is the halogenation of alkyl halides with active metals to give alkynes or alkenes. When vicino tetrahalide or dihalide are heated with active metals such as zinc or magnesium in the presence of anhydrous solvent like methanol or acetic acid, they lose halogen molecules which result in the formation of alkynes or alkenes respectively. Examples. Here we have 1,1,2,2-tetrachloropropane reacting with zinc in methanol under hot conditions to give propane. And here we have 1 and 2-dichloropropane which react with zinc in methanol to give a propene. Other reactions of alkyl halides are condensation and addition reactions. The first reaction is WURTZ reaction. WURTZ reaction is a condensation reaction of alkyl halides to produce alkenes. Alkyl halides react with the sodium metal to give alkenes. It produces long chain molecule with even number of carbon atoms. For the mechanism, confer preparations of alkanes. General equation, Rx reacting with R'(X), reacting with sodium in ether under hot conditions, it will give RR, R', R', RR', a mixture of alkanes. Let us have examples. Bromoethane reacting with another bromoethane with sodium in ether under hot conditions, it will give butane. Chloromethane reacting with chloroethane reacting with sodium in ether under hot conditions, it will give ethane, butane, and propane. The next reaction is addition of magnesium to alkyl halides to produce organomagnesium. Alkyl halides react with magnesium in dry ether or tetrahydrofuran to produce an organomagnesium, RMGX, or Grignard reagent. R may be an alkyl group, allyl group, alkenyl group, and so on. And X can be a halogen like chlorine, bromine, iodine. Example: 1-bromohexane reacting with magnesium in ether, it gives 1-hexyl magnesium bromide, which is an organomagnesium. Thank you.